Okay, the next presentation is excavation experiment of the earthworm type seabed exploration robot in actual sea area. It is presented by Tokoi, Mr. Tokoi. And so, okay, this paper is also present to you. Okay.
Yeah. I'm next presenter too. And thank you for your introduction and chairperson. I, Ryosuke Tokoi from Chuo University, will make a presentation on this title. Here's an outline on my presentation. First, I'd like to provide some background for my study. Recently, scientific investigation of the ocean has been actively conducted. Seabed mineral resources can be found at the bottom of the ocean. To utilize these resources, it is necessary to collect and analyze samples. Sampling of marine resources serves to clarify how marine resources are generated and distributed. To sample seabed mineral resources, vertical drilling was generally used. However, this method has two problems of low efficiency and large cost. To solve these problems, we aim to develop a seabed robotic explorer that can excavate horizontally and sample seabed mineral resources. At present, several drilling robots have been proposed as shown in Figure 1. However, many existing drilling robots are susceptible to this pressure, and drilled soil cannot be discharged out of the hole. Therefore, these robots cannot excavate deep underground. To solve these problems, we developed a drilling robot based on earthworm locomotion. Restricted motion of earthworm is the locomotion method as shown in Figure 2. This motion has some advantages on excavation. It enables to move narrow space and not to be susceptible to earth pressure and to discharge the soil through the body. We developed drilling robot which is propelled like earthworms, and this robot succeeded in vertical drilling of 430 millimeters into the ground underwater and bending drilling of 630 millimeters into dry ground. In a previous study, we developed a robot that can excavate underwater. However, our experiments were conducted in laboratory environment. Various grain sizes and waves are expected in real environment. So in this study, we confirmed the excavation performance through experiments in actual sea areas. Next, let me talk about the drilling robot. This robot is composed of two units, an excavation unit and propulsion unit. The function of excavation units is excavating the ground and transporting the soil. Propulsion unit moves like an earthworm by pneumatic cylinders and rubber tubes. Locomotion method of SEAVO II is as shown in Figure 5. Under State 1, all subunits were expanding. Under State 2, subunit 1 contracts and slides forward. Under State 3, subunit 1 expands and subunit 2 contracts and slides forward. Under State 4, subunit 2 expands and subunit 3 contracts. Under State 5, subunit 1 and 2 slides backward. Then the robot propels forward relatively. This locomotion method is less affected by earth pressure and easy to transport and discharge excavated soil. So SEAVO is structurally suitable for underground operations. For the actual sea area experiment, pressure-resistant and waterproof model case shown in Figure 6. A simple spec of the model case is shown below. Completely waterproof and it withstands deep sea water pressure of depth of 100 meters. Then let me talk about the experiments we conducted. First, the underground vertical excavation experiment. Objective of this experiment is confirmation of excavation performance and problems in actual sand ground. Figure 7-8 shows the experimental setup. Grain size of the ground is about 1 millimeter, and SEAVO excavated the ground not contained seawater. This is the relationship between time and drilling torque and black line, and excavation depth that was shows red line. 10 minutes after the start of the experiment, soil discharge was confirmed. And 15 minutes later, the entire length of the robot was successfully excavated. But after about an hour, the discharging outlet was completely filled and it became difficult to discharge the soil. So the experiment was stopped. This is a movie of an natural excavation experiment. The cable is in the way when the robot is propelling, so the cable is being adjusted as needed. Discussion of experimental results. Figure 10 shows the result of underground excavation experiment that conducted in a laboratory in previous study. In the field experiment, the drilling torque was an average about 20% higher than the laboratory experiment. The large drilling torque was caused by the large grain size of the sand and the gravel in the ground. The stagnation in drilling depth that is showed like this was caused by the cable being trapped. From this experiment, it was confirmed that the SEAVO can excavate in real sand ground. Second, gravel ground vertical excavation experiment. Objective of this experiment is confirmation of the relationship between excavation performance and problems in ground of different ground size. Figure 11 and 12 shows the experimental setup. Grain size of the ground is about 3 millimeters, and SEAVO excavated the ground not contained seawater. As a result, excavation was failed as shown in figure 13. Black line shows drilling torque versus time, and red line shows excavation depth versus time. A few minutes after the start of the drilling torque was drilling torque increased suddenly, and the excavation became impossible. At the end of the experiment, a large amount of gravel was trapped between the earth auger and the casing pipe, making it impossible to rotate. It was also found that gravel was trapped in the tip of the auger, increasing the excavation torque. Third, underwater vertical excavation experiment. Objective of the experiment is confirmation of the relationship between excavation performance and problems underwater. Figure 14 and 15 show the experimental setup. Laying of the ground is about 1 millimeter, and SEAVO excavated the ground underwater, like figure 15. Experimental results are shown in figure 16. Black line shows drilling torque versus time, and red line shows excavation depth versus time. SEAVO reached 75 millimeter excavation depth in 459 seconds. When the tip of the robot reached the ground, it could no longer excavate. The tip of the robot collided with gravel and other materials carried by strong waves, so the robot was unable to excavate. Finally, let me move on to conclusion. Which reached the following conclusion. It was confirmed that SEAVO II could drill in the sand ground of actual sea area, and it was confirmed that SEAVO II could not be excavated on gravel ground and underwater sand ground. As a future works, we will solve the problems found in this study and make it possible to excavate in various ground conditions. This is the end of my presentation. Thank you for your attention.
Thank you very much for your presentation. So, is there a question from audience? Or comment?
I have a comment. If you are trying to, there are two parts to your system. One is the excavation. The other one is this worm-like motion, right? Which you're using compressed air to move along. Why are you doing this? Because you're sort of penetrating to depths of about, the first results you showed were about 50 centimeter drill. And then later on about 5 millimeter. Couldn't that just be done with a single drill, which has no, worm-like action? It's just a motor and like an ordinary drill. So you just have a long drill. You could arrive at those kinds of depths simply by drilling with a drill bit. What is the reason for using this motion, the pneumatic beds?
First, we compared with consider the general sampling method is suitable for our objective, but this drill is so very long and very expensive to transport this drill or use like this drill ship. So this method is unsuitable for our objective. And so more small explorer is needed to sample the marine resources. But existing drill robots are like this, impacting type and screw type and bias-inspired type and so on. And that was penetrate into the ground or the impacting and screw by screw. But all the robot is susceptible to earth pressure. That means deeper the excavation depth, the friction from the borehole is gets larger. So deep underground, these robots cannot propel more. So not susceptible to earth pressure method is needed. So we focus on this method of earthworm locomotion. Okay, that is okay.
Motion overcomes the problem of soil pressure, does it?
Yeah, soil pressure.
Awesome.
It's overcome with soil pressure. Okay.
All right, thank you.
Yes.
Okay, so it's time to go. Oh, thank you very much.
Thank you.